Looking in the slide at a video of thermal fluctuations in a small system. These are micron-sized polystyrene latex spheres suspended in water and imaged on a video microscope. As a result of the small number of atoms hitting micron-sized particles from each side, the thermal fluctuations are immediately evident. Here is another example. In this case, what we've done to simulate a large number of particles is simply to run a simulation for a long time. So we have given particles in some fake box here an average velocity given by a half mv squared is a half kt, so they have the thermal average velocity on average, but their velocities are randomly distributed. After a large number of collisions, you see that they follow a distribution that looks something like a Gaussian. This distribution comes from putting a half mv squared into the Boltzmann distribution. It's called the Maxwell-Boltzmann distribution. We can calculate fluctuations directly from the partition function because it enumerates all the states of a system, and in particular tells us how many states lie close to the mean energy of the system. So the mean energy, it turns out, is given by the derivative of the log of the partition function with respect to beta, while the fluctuations are given by the second derivative of the log of the partition function with respect to beta. So let's see where this comes from. The mean energy of a system, thermal energy, is of course just defined by this Boltzmann weighted average, thus divided by the partition function to normalize it. If we look at the quantity minus d log z by d beta, we discover this is in fact equal to the thermal average energy. Why? Well, we can expand this as d log z by dz, which of course is just 1 over z, times dz by d beta. But dz by d beta just means pulling down a minus er from each term in the exponential, and this is nothing more than this component of the sum here. So this part comes from here, the 1 over z comes from here, and indeed then we see that this quantity is equal to the thermal average energy. What happens when you take the derivative of this quantity again with respect to beta? So when we do this, we have to expand the dz, d by d beta in terms of d by dz times dz d beta. When we do this then, the derivative with respect to z pulls down a term minus 1 over z squared, and then we have dz d beta all squared from the product of the two terms above. And then from the second term we get 1 over z and the second derivative dz d beta squared. Now you will recognize this is nothing more than the square of this term up here. So this is the thermal average energy all squared. If you look at this term, if we take the derivative with respect to beta of the partition function, we'll pull down another minus er, and the result then will be a plus er squared, e to the minus beta r, times 1 over z. What is that? That is simply the thermal average of E squared. So we have the difference between the thermal energy of E squared and the square of the thermal energy. This is just equal to the variance in the energy, or the thermal average of the square of the energy. To see this, just look at this expansion of the definition. So the fluctuations in energy are just given by the energy minus the thermal average energy. So if we square that and take the thermal average, this is what we have. This gives us then E squared thermally averaged minus the thermal average energy squared, thermally averaging that again doesn't do anything for us, minus twice the product of the two. But this is nothing more than minus 2e thermally averaged squared. So we see then that indeed delta E squared is given by d2 by d beta squared of the log of the partition function. Okay, so now we have a general expression for the fluctuations in energy of a system. Let's take a look at the ideal gas. We can rewrite this expression d2 log z by d beta squared as just minus d by d beta of the thermal average E. That was proved on the last slide. And this then is just the same as dt by d beta times d thermal average E by dt. This quantity here is the specific heat at constant volume. This quantity here we can work out the following way. T is just 1 over the Boltzmann constant times 1 over beta. And so if we take the derivative of this, we end up then here with this expression being equal to CV K Boltzmann T K all squared. So if we use the fact that from the equipartition theorem the thermal average energy of an ideal gas is 3/2 N kT, and of course the specific heat is the derivative of this, just 3/2 Nk, we can now substitute into this expression here and write for the ratio, so we take the square root of that expression, the ratio of the thermal energy fluctuations root mean square divided by the average energy. We get this expression here, where this is K squared T squared times N times 3 over 2, and that's all divided by 3 over 2 NKT. Within a factor that looks like the square root of 3 over 2 divided by 3 over 2, this is just 1 over the square root of n, the result that we quoted in chapter 1 without proof. So to show you numerically that a small system means large relative fluctuations, here is this factor 1 over square root of n plotted for a different n. 10 particles 30% fluctuations, 1,000 particles 3% fluctuations, Avogadro's number of particles 1 part in 10 to the 13 fluctuations. This argument applies to any extensive quantity that is proportional to the number of particles in a system.